What does it really mean for an AI to think? Today, we're diving deep into SQL and query optimization. Latency is cost. Throughput is revenue. The query optimizer is the central governor of modern data infrastructure. SQL processes exabytes daily, but most optimizers still use decades-old heuristics. The gap between actual execution and optimal plans widens with every new workload. A good query plan versus a bad one can mean 1000x resource consumption. At cloud scale, millions of queries per second means suboptimal plans have immediate cost and latency consequences. This is not a hardware problem, it's a software intelligence gap. Strategic focus, continuous query optimization, not just faster databases. But here's where it gets interesting. The static optimizer trap. Cost-based optimization assumes stable statistics and predictable resources. In cloud environments, this assumption breaks daily. Data skew, statistics drift, and concurrent workloads create plan regression. Missing cross-column correlations cause cardinality misestimates by orders of magnitude. Plan cache pollution forces frequent recompilations. DBAs still spend 30% of time manually tuning queries. Each new version adds more configuration knobs, but the approach remains reactive. Result: unpredictable latency spikes and 10x cost variation for identical queries. So what's the real problem? Let's talk about root causes of failure. Optimizers fail because they treat every query as an isolated event, blind to actual runtime conditions. Cardinality estimation errors compound exponentially across joins. Adaptive query processing is bolted on, not architected. Feedback loops are missing or too slow. Statistics are static snapshots that go stale within seconds. Without runtime feedback, the optimizer repeatedly makes identical mistakes across query template instances. In consequence, execution plans are rarely optimal on first run and sometimes never. This raises a critical question: the learning optimizer. We've reimagined the optimizer as a self-improving system that learns from every query execution. Embedded ML models predict cardinalities from actual data distributions. Reinforcement learning refines join ordering over time. Continuous feedback replaces static rule-based decisions. It does not rely on preset rules or DBMS version-specific heuristics. The system treats optimization as a continual optimization problem, not a one-shot, compile-time decision. It gets faster the more queries it processes. Now let's zoom in on adaptive query processor architecture. A layered design separates plan enumeration, execution, and feedback into independent, communicating components. Plan cache maintains alternative plans with confidence scores. Runtime engine collects operator-level metrics at millisecond granularity. Feedback store, time series database of performance observations. ML advisor, online model that updates cost coefficients. The architecture is event-sourced. Every plan change is logged and reproducible. Decoupling enables continuous evolution. New learning models or execution engines integrate without downtime. Here's something most people overlook: 5 core components. Each component addresses a specific failure mode of traditional optimizers. Learned cardinality estimator graph neural network using attention over table schemas to capture complex join correlations. Monte Carlo plan uoperator tree search over join orders. Runtime instrumentation streams, execution metrics. Performance aggregator window-based profiling. Re-optimization policy, online RL balances replanning cost versus expected gain. Together, they transform optimization from a compile time step to a runtime service. Think about this for a second. Query lifecycle. From SQL text to continuously optimized execution. Parse bind plan, ML assisted, execute, observe, feedback, reoptimize. incoming query parsed and bound. Optimizer proposes top K plans using learned costs. Execution with instrumentation. Plans include prediction confidence intervals. Metrics streamed to feedback store. Policy engine triggers re-optimization if performance cliff detected. New plan injected mid-query or cached for next run. The loop eliminates the optimize once, hope for the best paradigm. And this is where things get complex. Feedback engine deep dive. The learning loop converts execution telemetry into model updates, closing the gap between estimated and actual costs. Every query yields training points, actual cardinalities, CPU time, I/O. Drift detection triggers online retraining using a sliding window of recent queries to stay current without catastrophic forgetting. Models are versioned, allowing rollback if regression. The system learns workload patterns, peak hour dashboards versus nightly ETL. This is the mechanism that makes optimization adaptive, not just automated. But here's where it gets interesting: seamless SQL integration. Drop-in compatibility with existing PostgreSQL and MySQL ecosystems. No query rewrites, no application changes. It works with any ORM BI tool or SQL dialect. Fully compatible with PostgreSQL wire protocol and MySQL protocol, enabling transparent proxy deployment. Query hints become optional. The optimizer learns preferred access paths. Migration is a connection string change. Zero downtime migration, no restart required. Reduces adoption risk to near zero while delivering immediate performance gains. So what's the real problem? Let's talk about production impact. Real-world outcomes from financial services, e-commerce, and SaaS platforms. 10x reduction in P99 query latency. 40% lower cloud database cost. Zero manual tuning incidents in 12 months. 60% drop in DBA operational tickets. Automatic handling of data skew, node failures, and multi-tenant noise. Tail latency becomes predictable, enabling strict SLOs for customer-facing analytics. Cost per query predictability enables accurate capacity planning and budget guardrails. The system has processed over 50 billion queries, continuously improving. This raises a critical question toward autonomous databases. Query optimization is the first brain region. The next step is self-managing data infrastructure, auto-indexing, auto-partitioning, and materialized view selection, all driven by the same feedback loop. The optimizer will reel out data based on query patterns. Human role shifts from tuning to designing data models and SLAs. Vision, a database that provisions indexes before you notice a slow query, partitions tables as data grows and heals itself. This transforms the database from a passive store to an active performance system. Now, let's zoom in on the optimization mandate. SQL is the universal interface. The optimizer is its runtime intelligence. As data gravity intensifies, only self-improving optimization scales. The future belongs to data systems that learn, adapt, and govern themselves. This is not an incremental improvement, it's a shift in how we build and operate databases. It's the foundation of a new database era: self-driving, self-optimizing, self-healing. The mandate is clear: every query must become faster, cheaper, and smarter automatically.